This is K8BYP with the second transmission line and antenna video, or actually the second part of the first video because I ran out of time. In the first video, the point made was that on a current carrying conductor there are electric field lines extending out radially, and as a result of electron movement, not just electrons standing still, but in the case of movement, the magnetic field wraps around according to the right-hand rule. This is where hobbyists, technicians, and most engineers learn to fail to ever understand transmission lines and antennas, because they go on from here to embodying these fields and components, which we'll do next, and then think that everything can be analyzed by components. Well, transmission lines and antennas can't be, because they aren't components in transmission line and antenna operation. They can be taken out of context. Transmission line at 5 kilohertz is a capacitor. I've measured that with an LCR meter. I've measured the 135 feet of LMR 400-75 from my ham shack out to my 40-meter dipole with, I think it's a 5 kc LCR meter. It read capacitance. I went out and hung an additional capacitance on the end. It read it. This wonderful book, written by the best there is, or best there are, or were anyway, explains that that's only valid for low frequencies. And by the way, this book is where all this is coming from, or some of this is coming from this book. There'll be other sources brought in later. Electrostatic field, capacitance, capacitor. Two parallel metal plates separated by a dielectric or separated by nothing, even a vacuum. Apply a potential across the plates. What happens? Field lines are established between the two plates. Straight across, a little humped up along the edges. That's basic electricity. Disconnect the potential, the voltage source, the field's maintained. Simple proof. Charge up a capacitor and throw it to a friend. You all know that experiment. They grab it and get shocked and yell ouch and throw it back at you. Why? Because the capacitor stored a field. It did not store current. Current is the flow of electrons. When a capacitor is in steady state, there is no current flow, period. Capacitors don't store electrons. They don't store electricity. Current does not go through a capacitor. Capacitor dielectrics, ceramics, plastics are on the order of times 10 to the 14th to 20th power ohms. Extreme resistance. Why? We don't want leakage current, because leakage current results in low Q and eventually break down the dielectric and destruction of the capacitor. In the external circuit, under changing circuit conditions, such as this being discharged, slapping the juice to the capacitor, there's an external current. External laws of circuit analysis can be applied, but not to the fields. The fields are a different animal. They're not electricity, they're E fields, but they're not current flow. It's a terrible initial early on mistake to say that current goes through a capacitor. It looks that way, but it doesn't. That's the electrical field. Field contained with the voltage supply provided with the supply open, field maintained. Very important, because an inductor doesn't do that. An inductor, remember the magnetic field wrapping around a wire? That wire has a property of inductance. In a circuit of an inductor, a resistor, and a voltage source, when the voltage source is applied, a magnetic field is built around the inductor. And understand, we're not doing an experiment of connecting a dry cell to a big coil of wire at steady state conditions and using it as a magnet. That's electromagnetic. That's an electromagnet, and it's essentially steady state conditions. We're talking about AC and preferably RF conditions. When that voltage source is taken away, However, the inductor does not conserve that field. The field is contained only when the juice is applied. When the juice is taken away, unlike the capacitor, the field is not maintained. This is equilibrium with a charge between the plates electrostatically. Equilibrium here is attempting to balance the field with the voltage across terminals. When the potential source is taken away, the inductor, which was formerly positive on the left, negative on the right, flips polarity as that field discharges the opposite direction. Opposite field direction, opposite direction of current flow. And a resistor is shown there to give that current a path to go through. The maybe most elementary form of an antenna is this inductor with a switch. Not a resistor, but a switch, where the switch applies a voltage source, causes a current, the magnetic field charges, and then the switch opens infinitely fast so that no arcing occurs across the switch contacts, no energy returns to the circuit. Where does the magnetic field go? It doesn't fall on the floor. That's not the dust bunnies we sweep up and throw in a trash can. That energy is emitted off into space. The common term is radiated. That's a wrong term. Radiation's nuclear. Radiation became the subject of the nuclear field back in the 30s. US FCC uses the term emission, such as A1, A3, F1 emission from a transmitter. But that field is sent barreling off into space. There's been a posit in the past that antennas work by slowly charging and then suddenly something happens in a stepwise fashion. I've never seen an explanation of what happens. It's just left to that theory, and the theory's wrong. The theory is that there's a sine signal that charges, but then suddenly something happens for it to discharge. Well, a modification of that is what happens, and we'll get to that later. Fundamental equations. Unfortunately, we can't even get past basic Ohm's law without going through differential equations. Differential equations are calculus and then some. The way it's presented in college is horrible, overburdened, clumsy. If you want to learn it, understand it, get a book from the 1940s. Much simpler. The basic differential equation for a capacitor and inductor is shown here. A differential equation means that there are differentials on each side of the equal sign. Actually, in this case, they're both on the same side, but we move them. But here, for a capacitor, and dV and dt is the differential voltage over the differential of time. A differential is essentially, without getting into the calculus book, a differential is taking a zero interval of time, having a pulse, say a pulse is a second in duration. To analyze that pulse with calculus, we take a zero slice in time of that pulse and then integrate it. We get the total energy of the pulse. And that bears some explaining. The entire point of calculus here is what's known as area under the curve. Here's an XY graph with a square pulse function. It's easy to find the area. That's height times width. That's just geometry. But what if there's a pulse like this, and we need for some reason to know the total area under this curve, under this line? What if some space rocket science requires a precise calculation of how much energy is contained in that pulse? It's got to be exact. That could be important in switching power supplies to know how much energy is in that transient, because the transient suppressor has to be designed to eat that. If it's under design, the transient suppressor will blow up. I have some engineering background in that field. But this is not a rectangular or square approximation, it's a curve. So to be able to calculate the area under this curve and calculate it exactly precisely, we must know either a way to square this off with a line across here, find the square area here, and then find some way to approximate the area under this by maybe making that a triangle. That's inaccurate. There's a method called Riman Sums, which makes a group of tall, thin rectangles of a very narrow width, and finding the area of each of those as they go across, but that leaves air underneath this with little jagged pieces that don't fit into a rectangle. It's close, but it's no cigar. Calculus requires knowing the exact mathematical function of that curve, and if we do, that can be integrated over the limits of, if this is the x-axis, it's hard to write in the camera, of x from, say that's x1, and that's x10, for the limits of integration of x1 to x10, for this function, then for those x values in that function, integrating that formula for this curve will give the absolute, precise, extremely accurate area under the curve. And that's what we do to determine energy. How much energy is stored in the capacitor or an inductor? Well, if it's a sine function, focus. If it's a sine function, it's relatively easy to figure. These components are not sine components, they're exponential. And this is a big mistake in electronic education. These integrals are always approached, or usually approached, from the sine perspective when we get into circuits, because there's so much other complex stuff in circuits going on. But the sine function is extremely easy to integrate. These are really exponentials, and integrating exponentials gets to be a little bit uglier. In fact, considerably uglier. We sure don't want to do them by hand. But in the integral for the capacitor, the current, the total amount of current over time is the capacitance, as measured on a capacitance meter. C dV over dt, the differential of voltage divided by differential of time. And we can divide both sides by dt to get I dt equals C dV. That's a differential equation. There's a differential on each side. They're equated by the equal sign. The dV and the dt are the sine or cosine functions, so plug sine or cosine and integrate, and you got the answer, and it's easy. Anybody can do that with a high school math education. It's almost easier than algebra. For the inductor, the voltage is the inductance times the differential of current, not voltage. Capacitor, voltage. Inductor, current. Eli, ice. Remember that? Over the differential in time. Take dt over v dt equals L di. Same thing, plug in sine or cosine, integrate, easy, extremely easy. V dt equals L di. This is where Maxwell's equations come in to take these three-dimensional integrals of a current, assuming this is a length in an antenna arm, in a dipole arm, with a current flowing through it, which is a screaming error right there. Completely false. But it's an initial assumption. It's something. They use that, integrate these electrical and magnetic fields over 3 dimensions, x, y, and z. That gives the total amount of energy in the field, and by conservation of energy, that has to equal the energy. That has to equal the energy of the circuit. But it is a horrifying mistake to take the external circuit that drove that and pretend that that analysis applies to the antenna, because it does not. When trying to understand calculus, think of related rates. dV dt equals, or dV dt, comma, di dt. Each of those is a rate of change of a quantity. If there's no rate of change, it's a DC circuit. You can find any elementary calculus book and get that. 14 minutes, have to stop this video. Next will be video 3.